Welcome back, folks, and here we go again. We are about to finish Unit 4, and the last thing we want to talk about in this unit is something called intermolecular forces. Now, just to review, what have we been doing here? We've been looking at the geometry of molecules, and once we figure out the geometry of molecules, we can figure out the polarity of molecules, meaning is the molecule polar or is the molecule nonpolar? And now we're going to find we could use this knowledge about the polarity of molecules to predict intermolecular forces. So let us begin. Consider ammonia, carbon tetrachloride, selenium tetrabromide, and neon. Identify the intermolecular forces in each. Okay, here we go. We need some notes about intermolecular forces. So let's talk about intermolecular forces. And the place to start, of course, will be over here. Let's get a definition. What is a definition? This is a force of attraction. And what does inter mean? Between molecules. Okay? And so now we do not want to confuse this with something called intramolecular force. And what is an intramolecular force? Well, that is a force of attraction. What? Force of attraction. What does intra mean? Like intrastate, within a molecule. Okay? So intermolecular is a force of attraction between. Intramolecular is a force of attraction within. Let's consider water. Okay, let's say we have some water and we have an oxygen and a couple hydrogens on that. Let's put a couple unshared electrons on here, right? And let's say we had another water molecule, and here's that water molecule. Oops, let's go with the black here. Here's that oxygen, and here are my hydrogens, and here are the unshared pairs. Good. Now we have two types of attraction occurring. We have this area right here, right? And that's where my hydrogen atom is overlapping my oxygen. And this is a bond, right? We would call this a covalent bond. And this is a covalent bond. And notice, where does that occur? Does that occur between the molecules or within? Well, that is within, and so that would be what? An intramolecular attraction, intramolecular force. Good. But there's also an attraction between this unshared pair and this hydrogen. And notice, it is not within the molecules, it is between the molecules, because here's one molecule, here's a second molecule, so this attraction is between two different molecules, so that would be what? An intermolecular force. And we'll get into the details of what type of intermolecular force this is a little later. Good. Just wanted to illustrate clearly the difference. So when we talk about covalent bonding in carbon tetrachloride, that's intramolecular because it's within the molecule. If I talk about London dispersion forces between my carbon tetrachloride, then that would be an intermolecular force. Good. And I kind of gave you a hint about something, right? We have different types of intermolecular forces. So let's talk about the types of intermolecular forces, and we're going to need some space. Yoink! So one type is something that we call London dispersion forces. Okay, so what are London dispersion forces? These are an intermolecular attraction, in which the continuous motion of electrons form instantaneous, temporary dipoles. Okay? And what is a dipole? Meaning that is a temporary polarity within the molecule. So if I have, let's say I have a hydrogen here, and a hydrogen here, and a hydrogen here, and a hydrogen here, right? And these each have one electron, but there's a point at, oh, excuse me, we have to have these bonded, sorry. Yoink, 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 yoink. Right, so I have a hydrogen here, overlap and overlap, hydrogen, and then a hydrogen here and here, right? Good. Now, most of the time, those electrons are probably going to be where in the middle here. But it's possible that for a short period of time, they could be over here. And so if they're over here, what happens? This becomes a little negative, and this becomes a little positive. Well, if this becomes a little negative, what's that going to do to the electrons in this hydrogen? Well, it's going to force them over here. And so now this becomes a little positive, and this becomes a little negative. And this will happen across all my hydrogens, and so I get a temporary attraction between the positive and the negative in the hydrogen. Now, once again, this is instantaneous. It's not that these electrons stay here permanently because they're always moving around. Most of the time, they're going to be found, what, in between my hydrogens, but for a time being, they can bounce around. And so the bouncing around of these electrons can lead to temporary dipoles being formed, and that is what temporary, boy, I just destroyed that, didn't I? Temporary dipoles. Okay, so intermolecular attraction in which the continuous motion of electrons form instantaneous temporary dipoles. Those are London forces, and they occur in all things, all matter. So this is in all atoms, this occurs in all compounds, it occurs everywhere. Next, let us consider what we call dipole-dipole interaction. Dipole-dipole interaction. Good, and what is dipole-dipole interaction? It is the attraction, the intermolecular attraction, between the positive side or pole of one polar molecule and the negative pole of a neighboring polar molecule. Now you'll find out that can also apply to, doesn't necessarily have to be a polar molecule, could be an ionic molecule, but for us, we're going to focus, an ionic ion, we're going to focus on molecules here. So consider our HCl, right? We have HCl, and my chlorine is pulling on those electrons more than my hydrogen. And so we say, hey, this is linear. It's symmetric, but I don't have the same atoms on both sides, so it's a polar molecule. And since the electrons are closer to my chlorine, it gets what we call a partial negative charge. And on the other side, I have a partial positive charge. So that means over here by my hydrogen, it's positively charged, not permanently, but it has a positive, it's more positively charged than neutral, and my chlorine is more negatively charged. Then what happens if I have another HCl? Well, this side's negative, this side's positive, and once again, this side's positive, this side's negative. What do you know about the relationship between positives and negatives? Well, there's going to be an attraction here. And this attraction between the positive side of my HCl and the negative side of my chlorine is a dipole-dipole attraction. Now, this occurs only in polar molecules. So all that work we did last lecture about determining polar molecules, this is why it's so important, because it helps us understand what kind of intermolecular forces are occurring. And then finally, we have something called hydrogen bonding. Hydrogen bonding. And I hate the name of this because one would think anytime you have hydrogen bonded to something, you would have hydrogen bonding. But no, this is not correct. This is an intermolecular force of attraction. Intermolecular force of attraction. And maybe the intermolecular is redundant at this time, right? Force of attraction between, now there's two things that this is between one, a hydrogen atom, between hydrogen bonded to nitrogen, oxygen, or fluorine, and an unshared pair of electrons on a neighboring molecule. For me to have hydrogen bondings, I must have both these. I have to have hydrogen bonded to a nitrogen, or hydrogen bonded to an oxygen, or hydrogen bonded to the fluorine in my molecule, and I must have an unshared pair on my neighboring molecule. Okay, so what's the perfect or the typical example is water, like we drew before, right? I have oxygen here, and that oxygen is bonded to two hydrogens, and there's an unshared pair. There's two unshared pairs of electrons on my oxygen. Here's my oxygen. Here are my hydrogens, right? What do I have? I have a hydrogen bonded to an oxygen. So that means that this hydrogen is essentially just a proton because the oxygen is pulling these electrons very tightly. And so this has a positive charge, a partial positive. Over here's a partial negative, here's a partial negative, here's a partial positive, right? Associated, this partial positive is associated with my hydrogen, partial negative with my unshared pair. And so there's attraction then between this hydrogen and this unshared pair. Now notice, this hydrogen is on this molecule, this unshared pair is on this molecule, so it's an intermolecular force of attraction. And so this is what we would call what? Hydrogen bonding. But notice, we do not call this hydrogen bonding. That is not hydrogen bonding, even though this is a hydrogen and this is an oxygen. Why not? Because that is intramolecular. Hydrogen bonding is between the hydrogen on one molecule and the unshared pair on another. It is between two molecules. Great. All right. Let's go and answer our question. Well, really, before we answer our question, I think what we need to do here is, let me give you a decision tree. How do we go about figuring out intermolecular forces? Here's the way I do it. First of all, I say, is it a substance? That's the first place I begin. Is it a substance? If the answer is yes, then London dispersion. I have London dispersion. Well, that means just about everything. Yes, it is. If it's not light, then it probably has London dispersion. Next question. Is molecule polar? And if it is no, then the only thing it has is London. If it is yes, then it has London and dipole-dipole. So it has London and dipole-dipole if it is polar. And then we ask another question for it. Does it have hydrogen bonded to fluorine, or hydrogen bonded to oxygen, or hydrogen bonded to nitrogen, and an unshared pair? Does it have that stuff? If the answer is yes, then we have London, and we have dipole-dipole, and we have hydrogen. bonding? If the answer is no, then we only have London and dipole-dipole. That's how we go through this. That's my thought process. All right? Good. So let's do this. Ammonia. Let's go back and refresh our memories. Ammonia is polar. Carbon tetrachloride is non-polar. Selenium tetrabromide is polar. And neon is neon. It is not a molecule at all, so this is only an atom, right? Okay, if it's let's look at this for a second. Here is my ammonia. So we have to look at this a little bit. It's polar, okay? So that means, number one, first of all, it is something, right? So it has London. It's polar. That means it has what? Dipole-dipole. And now let's ask the third question. Does it have hydrogen bonded to nitrogen? Sure does. Does it have an unshared pair? Sure does. That means it also has hydrogen bonding. So ammonia has all three. Carbon tetrachloride, well, it is nonpolar. And if it's nonpolar, that means it only has one option. If it's nonpolar, what does it have? London. And then we stop. Selenium tetrabromide. Selenium tetrabromide, that's a nice S, Kendall. Yeah, selenium tetrabromide. Well, we said it's polar, so that means it has London and dipole-dipole. Does it have hydrogen in it? No, there's no hydrogen, so it can't have hydrogen bonding, and we're done. And then finally, neon. Neon is not even a molecule, but it is a substance, and all substances have what? London. By the way, you can see I sometimes abbreviate London dispersion with LD, and that's certainly acceptable. All right, you guys try these and bring me back when you're ready. Shouldn't have been too hard. Nitrogen, right? This is what nitrogen looks like. Is it polar? The answer is no, it's not polar, so it has London. Bromine tetrafluoride. Bromine tetrafluoride is what? If we remember our work from before, it is indeed polar. And if it's polar, well, let's make sure it's polar. Maybe I better draw the picture. Let's see. 5, 6, 42 electrons. Yes, I need 46 electrons. So if I did this right, we're going to have something like this, right? 5, 6, 42 electrons, right? Not, those are F's, sorry. F, 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 F. And we have our electrons around them. And each, so that's, which is at 8, 16, 24, 32, 40. And I need to have 42. So this is what? This looks to me like it is square pyramidal. Square pyramidal is polar. If it's polar, I have London and dipole-dipole. And there are no hydrogens here, so it can't have hydrogen bonding. Here we go. CH4. Well, this is tetrahedral. I have the same atoms around, so this is nonpolar. If it's nonpolar, the only thing I have if it's nonpolar is London. Well, what about hydrogen bonding? Well, no. I don't have hydrogen bonded to what? It's got to be bonded to oxygen, nitrogen, or fluorine, and it has to have an unshared pair. This does not have any of these three bonds, nor does it have an unshared pair, so it is not hydrogen bonding, and you can't have hydrogen bonding unless it is polar. Good. And then finally, boron trifluoride. Remember, boron trifluoride looks like this, right? And this is what? Trigonal planar, which means it is nonpolar. If it's nonpolar, then it is London. Okay, great. So those are our answers. Consider hydrochloric acid, HCl, or hydrogen chloride, and water. Explain why water has a higher boiling point than that of HCl. Okay, we're going to add one more thing to our set of notes. And, ooh, boy, we're going to have to take a circuitous route here. Keep going. Woo-ha! Yee-ha! I think we're almost there. Nope. Oh, boy, what a long set of notes this is. Okay. We want to talk about IM forces, and IM means what? Intermolecular forces and melting point, boiling point. Okay, and it's really simply the stronger the IM forces, the higher the melting point and boiling point. Okay, it's that simple. Why is melting point so high in something? It's because it has stronger intermolecular forces. That is what causes the melting point to be high, is you have to overcome these stronger intermolecular forces. Good, so we can answer this simply. Okay, explain why water has a higher boiling point than HCl. The easy answer is water has stronger IM forces. That is the simple answer. Now why? Well, the why on this is, okay, this is polar, and this is polar. Got it? What else? Well, does this have hydrogen bonding? No, because I must have oxygen, nitrogen, or chlorine. What about water? Water has hydrogen bonding. So my HCl has only dipole-dipole and London, and my water has London, dipole-dipole, and hydrogen bonding. And so it has stronger intermolecular forces. And so why, if the answer is why, to justify this, because H2O has London, dipole-dipole, and hydrogen bonding, which together are stronger than the London and dipole-dipole in HCl. That's the perfect answer. Well, perfect, I don't know. That's a hard thing to say. Okay, finally, last slide, and then we're done with the unit. Consider solid water, magnesium oxide, silicon 4 oxide, and magnesium. Describe the bonding in each solid. Okay, we want to spend a little bit of time talking about bonding in solids. Not much. Bonding in solids. Okay, and there's 4 types that I want us to consider. One is what we already know, and that is molecular. Molecular bonding is a bonding in a solid. We'll call it solid bonding, in which molecules are held together by intermolecular forces. Intermolecular forces, the things we are just talking about. London dispersion, those kinds of things. These are weaker, actually. These forces are weaker than other bonding that we're going to talk about. And since they're weaker, what do we know about their melting points, for instance? They have lower melting points than other solids. Good. And an example here would be water. Next, let's go with a metallic bonding. And what is metallic bonding? This is in metals. This is bonding between metals in which metal cations are surrounded by a sea of valence electrons. And these have high melting points and boiling points, and they are relatively soft and malleable, right? Now, what are my examples of this? This is, any metal, iron, aluminum, sodium. And the way to visualize this is, say we have something like sodium as a metal. Really, we've got a bunch of sodium cations, but they haven't lost their electrons. Their electrons are kind of free floating around the sodiums. And so that's what makes our metallic bonds. Also, this is what makes it what? Why do we have good electrical conductivity? Because these electrons are relatively free, and so when I hit them with another electron from outside, they can easily force electrons to continue flowing, and so we can get electrical current. Third, something we know about, right? Ionic. And ionic bonding is what? Bonding between a cation and an anion, forming what? A lattice. And this is relatively strong, and since it's relatively strong, they have high melting points, high boiling points, and they are hard and brittle. Hard and brittle. And any ionic compound, sodium chloride, magnesium oxide, and so forth. And then the last one we want to talk about is okay, here we go. And it is something called covalent network. Okay, now what is a covalent network? A covalent network are solids in which atoms are held together by covalent bonds. We know what that means. That means they're sharing electrons by covalent bonds in large chains. Okay? And so what are examples of this? Hey, carbon as a diamond, carbon as graphite, silicon dioxide. These are all forms of covalent networks. And how do you know that? You just memorize them, folks. Just memorize that diamond, graphite, silicon dioxide are covalent networks. Very high melting points. As you know, with diamonds, they are very hard, right? Good. So that's really our overview of bonding in solids, 4 kinds: molecular, metallic, ionic, and covalent network. And what is water? Water is molecular. Magnesium oxide, that is a metal and a non-metal, so that is ionic. Silicon dioxide, I memorized that just now. It is covalent network. And magnesium, piece of cake, that's a metal, so it is metallic. Okay, and which would have high boiling points? This would be high, 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 low. All right, okay, that's it. We are done. And next time we'll move on to the next unit 5. Bye-bye.